When you think about metal stamping, it seems pretty straightforward, right? A huge press comes down, wham, and a perfect little part pops out. But what happens when that part isn't so perfect? Well, it turns out the answer is hidden in a secret language, written on the one thing most factories just throw away. I mean, just look at the difference here. On one side, you've got this clean, perfectly formed component, exactly what you want. And on the other, yikes, it's a disaster. The edge is all rough and jagged with this nasty, sharp burr. What's crazy is that both of these came from the very same machine, maybe just seconds apart. So what gives? What's the actual difference? Often, it's a microscopic error, a tiny shift in alignment, or a tool that's just starting to get dull. But an error like that over a huge production run can lead to millions of dollars in scrap parts, product recalls, and killer downtime. So the real question is, in a factory that's just roaring with machinery, how on earth do you find the source of such a tiny mistake? So, where do you even start looking for the cause of this million-dollar mistake? Your first instinct, probably, is to go check the biggest, most complicated parts of the system. But here's the thing, and you might be surprised to hear this. The answer almost never lies in the giant press itself or in those fancy computer controls. Sure, they're important, but they usually just tell you that a problem exists. They don't tell you why. The secret, the real clue, is actually hidden in plain sight. It's in the carrier strip. You know, that metal skeleton that's left over after all the parts are punched out. This is the stuff that most people just sweep up and toss into the scrap bin. But for a trained eye, it's basically a detailed report card for the entire stamping process. To find these clues, we have to learn how to read the evidence, and that all starts with learning the alphabet of a metal cut. You see, every single time a punch shears through metal, it writes a little four-part story on the edge of that material. Okay, so here's how that story breaks down. First, you get the rollover. That's where the punch first pushes in and creates a little rounded edge. Second is the burnish, this smooth, shiny band where the tool is literally slicing the material. Third is the fracture, which is a rougher, kind of angled zone where the metal finally breaks. And last, you have the burr, that tiny, unwanted lip of metal at the very bottom. Now, of these four zones, the burnish is by far our most important piece of evidence. And you might ask, why? It's because that shiny band is the only part of the entire edge that makes direct, intimate contact with the tool. Its depth tells us exactly how that tool is behaving and how the metal is reacting to it. So, in a perfect world, a healthy, well-balanced cut leaves a very specific signature. That shiny burnish should make up about 1/3 of the edge's total thickness, and the rough fracture part, that should be the other 2/3. This 1-to-2 ratio is our golden standard. It's the baseline for a perfect cut. Okay, so now that we know what good looks like, we can finally put on our detective hats. It is time to interrogate the evidence and crack the case of that bad part we saw at the beginning. So, what if we look at the edge of one of our scrap pieces and the burnish isn't nice and uniform? Let's say it's really deep and shiny on one side, but it's super shallow, almost non-existent on the other. What in the world is that telling us? Well, that right there is the classic #1 dead giveaway of a critical error, punch-to-die misalignment. All it means is that the clearance, that tiny critical gap between the cutting punch and the die, isn't even all the way around. It's way too tight on one side and way too loose on the other. Okay, great. So we know what the problem is. It's misalignment. But honestly, that's only half the battle. To actually fix it, we need to know which way the punch has shifted. Is it north, south, east, or west? Well, don't worry, the evidence holds that answer too. Let's look really close at that scrap slug, that little round piece that got punched out. You're going to notice a very distinct, shiny, polished area on one side of its edge. That one little spot, that's our smoking gun. It is about to tell us everything we need to know. So here's the big secret. The side of the slug with that super shiny, heavily burnished band is the tight side. It's the area where the clearance is too small. That shiny spot basically acts like a compass, pointing you directly toward the direction of the misalignment. If it's on the north side of the slug, you know for a fact the punch has shifted north. It is that simple and that incredibly powerful. And this same logic, this same detective work, it applies to other defects too. You see a heavy burr on just one side, that confirms our misalignment theory. But what if the burr is heavy and totally uniform all the way around? Well, that points to a different culprit, a dull tool. What if slugs are sticking to the punch when they come up? That's probably magnetism from a recent tool sharpening, or even just suction from using oil that's too thick. Every clue points to a culprit. Understanding a single cut, that's one thing. But the real mastery, the next level, comes from reading the entire story of how a part is made, from the very beginning to the very end. See, in modern manufacturing, parts aren't just made in one big hit. Instead, a long strip of metal, a progressive strip, moves through the machine. And different things happen at different stations, all in a sequence. Piercing here, forming there, trimming a bit later. This progressive strip tells a chronological story, and we can read it. So let's trace this one. At station 1, a nice clean hole is pierced. Everything looks good. But by station 3, a tiny burr starts to form, and then it gets flattened out. Then 2 stations later, at station 5, that flattened burr actually gets pressed into the part's surface during a forming operation. By the time it gets to the end, at station 7, the final part has this mysterious mark on it and nobody knows why. But by reading that strip from beginning to end, we can see exactly how that tiny, almost insignificant burr from an early station snowballed into a critical surface defect many steps down the line. This is so much more than just problem solving. It's about gaining predictive power. You can spot the tiny error before it becomes a big, expensive one. This really forces you to completely shift your perspective. It all comes down to what the experts in this field say. The stamped strip is not scrap. It is a real-time process control chart telling a detailed story. Honestly, it is the cheapest, most effective, and most brutally honest feedback you can possibly get about the health of your entire process. Ultimately, this whole idea is about so much more than just stamping metal. The principle here is universal, and it really makes you wonder, what other so-called waste products or overlooked details in our own work, or, hey, even in our own lives, are actually packed with hidden information, just waiting there for us to finally learn their language?